continue to expand on our understanding of Newton's law of universal gravitation. Again, this is Newton's law of universal gravitation. And at the time it was new because people thought that the laws that govern how things happen on the earth were different than how they govern things that happen in the heavens. This is the law of universal gravitation. Newton said that this law applied to things not only on the earth, but in the heavens also. But in order for this new law to be valid, it had to coincide or work with or fit with the previous things that we knew about the forces between objects. And if you recall, we did a calculation where we determined the force of gravity of an object on the surface of the earth, or the person on the surface of the earth, and using Newton's law of universal gravitation. And it coincided with how we already knew to determine the force of gravity of an object on the earth, because the acceleration of an object on the surface of the earth is 9.80 meters per second squared. So when we use Newton's law of universal gravitation and we use this force of gravity equation, we came up with the same answer. So they fit, they coincide. Now another thing to remember is that this mass in the law of universal gravitation is called gravitational mass, and this mass in the force of gravity equation using the acceleration of gravity is called inertial mass, because it's using acceleration, how difficult it is to take an object to move. This object in this equation doesn't have to be moving at all. It still has mass. So this is gravitational mass, this is inertial mass. A little derivation. Since Newton's law of universal gravitation had to fit with all previous things, Kepler's third law was a previous law about planetary motion, so Newton's law of universal gravitation had to also fit with that. So if we take a look at this, this is the sign. Again, you can pause this video so you can catch up with the derivation and stuff. I'm just going to talk my way through it here a little bit. This is the Earth going around the Sun. It's mostly a circular orbit. It's technically an elliptical orbit, but it's also circular, which means that there is a centripetal force causing that object to move in a circular path. That centripetal force is due to the gravitational attraction between the Earth and the Sun. That's the only force acting on us. So if we add up all the forces acting on the Earth, we get the centripetal force. There's only one force, that's the force of gravity. So those two forces are equal to each other. Remember, Kepler's third law is period squared over r cubed. So how can we fit this force of gravity in with Kepler's third law? Well, let's take a look at this little derivation. This centripetal force is the mass of the object that's moving in the circle, which in this case is the Earth. It's the mass of the Earth times the velocity of the Earth squared over the distance the Earth is from the Sun, center to center, mv squared over r. That's equal to the gravitational force, g times the mass of the Earth times the mass of the Sun over the orbital radius of the Earth squared. I cancel things that are common. This is the mass of the Earth that cancels out. This is the orbital radius of the Earth. This cancels one of these, that's orbital radius squared. And then we have this equation. From here, we have the velocity of the Earth squared is equal to g times the mass of the Sun over the orbital radius of the Earth. Let's take a look at this velocity. We know that the equation for the velocity of an object moving in a circle is the circumference divided by the period. But this is velocity squared, so I'm going to square both sides of this equation. This would be velocity of the Earth squared. 2 squared is 4. Pi squared times orbital radius of the Earth squared over period squared. So this quantity here is the same thing as the velocity of the Earth squared. So I'm going to take this quantity, put it in this equation, and substitute it in for the velocity of the Earth squared. So it's going to be 4 pi squared re squared over period of the Earth squared equals g times the mass of the Sun over the orbital radius of the Earth. I'm going to try and get all the periods and the radii on the same side of the equation. So I'm going to move this period to this side of the equation, multiply both sides by period squared, put it in the numerator, divide both sides by radius squared, put it to the denominator. Move this, divide both sides by g times mass of the Sun. So it moves over to this side of the equation. So I get this quantity on the left side, and look what I have here. Period squared over radius of the Earth cubed. Because period squared goes on top, this radius of the Earth squared there, times radius of the Earth, that's radius of the Earth cubed. And there it is, Kepler's third law. So what we see here is that the law of universal gravitation fits well with Kepler's third law. And this quantity here, that is the constant in Kepler's third law, at least the constant for anything orbiting the Sun. All planets orbit the Sun, period squared over r cubed equals some constant. Well, this is the constant. 4 pi and g are all constants, they don't change. And the mass of the Sun is the central object. Anything that's orbiting the Sun, that mass is the same. So this is a constant that's equal to Kepler's third law. So Newton's law of universal gravitation fits Kepler's third law. Let's keep expanding on law of universal gravitation. We're going to use this derivation but not go all the way through it. Let's see what we end up getting. Let's take a look at this little velocity of a satellite. All of you know about satellites that orbit the Earth. Well, a satellite is really just a horizontal projectile shot at a very fast speed. So let's see what we mean by that. We have a cannon and we shoot it horizontally. That cannonball is going to follow a trajectory, a parabolic path, and land at some distance from that cannonball. Notice if we shoot that cannonball even faster, it's going to land a further distance, a larger range, still in a parabolic path. Shoot even faster, it'll fall further, even faster it falls further, even faster it falls even further. If we shoot it fast enough, it's keep falling around the Earth until it hits the same place, then it keeps going around. If we shoot a projectile horizontally fast enough, that projectile will orbit the Earth at some velocity. Well, again, if it's moving in a circular path, it has a centripetal force, and that centripetal force is due to the gravitational force between the Earth and whatever satellite is orbiting that Earth. This is the centripetal force on the satellite, so that's the mass of the satellite times the velocity of the satellite squared over the orbital radius of the satellite. And the orbital radius of the satellite is simply from the center of the Earth to where that satellite is. And this is equal to the force of gravity, which is g, times the mass of the Earth times the mass of the satellite divided by the orbital radius of the satellite squared. We can cancel some things out just like we did before. This is the mass of the satellite. That cancels out. We're left with the mass of the Earth, which is the central object. And this orbital radius of the satellite cancels one of these. And then again, we have the velocity of the satellite squared is equal to g times the mass of the Earth over the orbital radius of the satellite. We take the square root of both sides. We want the velocity of the satellite. We want to determine how fast the satellite has to be moving in order to orbit the Earth. Take the square root of this. This simply becomes the velocity of the satellite equal to the square root of g times mass over radius. Now, we use the Earth as an example. It could be anything. I could have used this central object as the sun, or I could have used Jupiter, or I could have used any planet like Mars or the moon. We could have figured out the velocity of a satellite orbiting any central object. So this mass, this m, is the mass of the central object. And this r is the orbital radius of, I'll put satellite there, orbital radius of the satellite. So if there are many satellites, many man-made satellites that orbit the Earth, so it could be any man-made satellite, its distance from the center of the Earth, or it could be the moon. The moon is a natural satellite, so it could be the distance the moon is from the center of the Earth, that value right there. But this m is always the mass of the central object, whatever the satellite is orbiting. It could be the Earth, it could be the sun, it could be Jupiter, it could be any planet or any object. So let's take a look at acceleration of gravity, because we know if somebody is on the surface of the Earth, we'll say this is a person, that this person has an acceleration of gravity of g, 9.80 meters per second squared, due to the force of gravity between the Earth and that person. But if this person is here, like an astronaut, well, this person has a larger distance from the center of the Earth. This distance is simply the radius of the Earth, which we'll call the orbital radius of the person. Now this orbital radius of the person is not the radius of the Earth, it's the distance from the center to that person. The force of gravity on this person is less out here than it is here. Since the force is less, this person has to have a different acceleration because of Newton's second law. So let's see how we can figure that out. Again, we've already shown that the force of lowercase g is equal to the force of the capital G. This is Newton's law of universal gravitation. This is mg. So we'll put those equations in here. This is the mass of the person or object times the acceleration of gravity is equal to g times the mass of the Earth times the mass of the person or object over the orbital radius of the person squared, the distance the person is from the center of the Earth in this case. Again, we can cancel similar things out. This mass of the person cancels. And we have this g, the acceleration of gravity, is equal to the constant g times the mass over r squared. Again, this mass, this m, is the mass of the central object. And this r is the orbital radius of the object. how far it is from the center of the central object. It can be a person, it can be a satellite, it can be anything. But remember, the mass of the object or the person doesn't matter. Just like on the surface of the Earth, doesn't matter what the mass of the object is, its acceleration is always 9.80 meters per second squared. So this is the acceleration of gravity of any object, anywhere in the universe, around any central object. Let's take a look and see if that works for the acceleration of gravity on the surface of the Earth. Remember, the mass of the Earth is 5.98 times 10 to the 24th kilograms. Orbital radius of the Earth, which in this case, if the person is on the Earth, is the same as the orbital radius of the person, is 6.38 times 10 to the 6 meters, so 3. And we want to know the acceleration of gravity on the surface of the Earth. Well, we can use this equation. We know it should be 9.80 meters per second squared because anything on the surface of the Earth, we already know it should be 9.80 meters per second squared. Let's see if we get that same answer. So we have G, acceleration of gravity on the Earth, equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the central object. The central object in this case is the Earth. So it's 5.98 times 10 to the 24th kilograms divided by the distance the person is from the center of the Earth, which in this case is just the radius of the Earth, which is 6.38 times 10 to the 6 meters. Don't forget to square that value down there. Now, let's calculate this out and let's see what we get. This is the acceleration of gravity on the surface of the Earth. I'll put this in my calculator. We'll see what we get. So it'll be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24th divided by 6.38 times 10 to the 6 squared. And we get 9.799. We'll round that to 9.80 meters per second squared, acceleration of gravity on the surface of the Earth. Now, if we want to know the acceleration of gravity at some distance above the surface of the Earth, everything would be the same except for that number right there. We simply have to determine how far that object is from the center of the Earth and put in that new distance, and we get a smaller acceleration of gravity. Let's do some example problems using these equations. The first one is, what is the acceleration due to gravity at a height of 9.50 times 10 to the 6 meters above the Earth? We're going to draw a diagram. This is the Earth, and we have some height above the Earth. We don't have to have an object there because the mass of the object doesn't matter. Remember, the acceleration of gravity doesn't depend on the mass of the object. And so we have the height, that's the distance from the surface of the Earth. This is the height, h equals 9.50 times 10 to the 6 meters. We want to know the acceleration of gravity at that height around the Earth. Again, the equation is acceleration of gravity is equal to g times the mass of the central object, which in this case is the mass of the Earth, over the orbital radius of, or the distance that that object is from, or that point is from the center of the Earth, that r, squared. Don't forget to square that. So now, this r is the distance from the center of the Earth, from here to there. And that r is equal to the height plus this distance, the radius of the Earth, plus the radius of the Earth. The information that we know the mass of the Earth. We can look it up on our data table. We can look up the mass of the Earth and the radius of the Earth on there. Mass of the Earth is 5.98 times 10 to the 24th kilograms. The radius of the Earth is 6.38 times 10 to the 6 meters. So we put these values in. G equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by the distance from the center of the Earth. Well, that distance is this r, so we have to add the height to the radius of the Earth. So this r is the height, 9.50 times 10 to the 6 meters, plus the radius of the Earth, 6.38 times 10 to the 6 meters. If you add those together, you should get 1.59 times 10 to the 7th meters. So that's what goes in here, 1.59 times 10 to the 7th meters. Don't forget to square that. If you do that calculation, you can pause the video and do the calculation yourself, see what you get. I get 1.58 meters per second squared. And it should be less than 9.80 meters per second squared because you're quite a ways away from the Earth itself. Let's take a look. What is the velocity of a satellite at this point? So now we're solving for the velocity of the satellite. Again, it doesn't matter what the mass of the satellite is because the mass of the satellite cancels out with the derivation that we did. The equation is velocity is equal to the square root of g times the mass of the central object, which is the mass of the Earth, divided by the orbital radius of the satellite. So we have this information. So velocity is equal to the square root g, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, divided by the orbital radius of the satellite, which is this distance that we have right here, 1.59 times 10 to the 7th meters. If we do that calculation, again, you should pause the video and see what answer you get. If we do that calculation, we take this number times this number divided by this, and we're going to take the square root of that answer, which you get 5.01 times 10 to the 3rd meters per second for the velocity of that satellite. Let's do problem number 2. What is the acceleration due to gravity on Mercury? All right, so basically, draw a diagram. This is Mercury. We have some object or a person on the surface of Mercury. So the distance that person is, this is the orbital radius of where we're located, which is the radius of Mercury. Again, we can look that up on our data table. And the radius of Mercury is 2.44 times 10 to the 6 meters. The mass of Mercury, look up on the data table again, is 3.30 times 10 to the 23rd kilograms. And we want to know the acceleration due to gravity on Mercury. So the acceleration equation, Mercury is equal to g times the mass of Mercury, Mercury is a central object, divided by the distance you are from the center of Mercury, which in this case is the radius of Mercury squared. So this is going to be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of Mercury, 3.30 times 10 to the 23rd kilograms, divided by the radius of Mercury, 2.44 times 10 to the 6 meters, all squared. Again, you can pause the video if you can do that calculation correctly, and you should get 3.70 3.70 meters per second squared, not times anything. Last problem. How fast must a satellite travel to orbit the Earth at a height of 2 times 10 to the 7 meters? So now again we have the Earth. This is the Earth. We have a satellite, some height above the Earth. Say this is the height. 2.00 times 10 to the 7 meters. We want to know the velocity of that satellite. Well, the equation we have is the velocity of the satellite is equal to the square root of g times the mass of the central object. The mass of the central object is the Earth, divided by the distance we are from the center of the Earth. And this is from the center of the Earth to that satellite is r, which is equal to height plus the radius of the Earth. We know the radius of the Earth. We used it many times now. The radius of the Earth is 6.38 times 10 to the 6 meters. So we're going to get this r is equal to the height, 2.00 times 10 to the 7th meters, plus 6.38 times 10 to the 6 meters. We get that r to be 2.64 if we round times 10 to the 7th meters. We put that into the velocity equation. The velocity of the satellite is equal to the square root 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the Earth, We use that several times too. The mass of the Earth is 5.98 10 to the 24th kilograms, divided by r, the distance we are from the center, 2.64, 10 to the 7th meters, is all square root of that. We get the velocity of that satellite. Again, you can pause the video, do that calculation. Get 3.89 10 to the 3rd meters per second for the velocity of that satellite. One last thing we have to do, that's called gravitational fields. I'm sure all of you have heard about gravitational fields and science fiction movies and stuff. Well, let's find out exactly what that is. Let's say we have the Earth. This is the Earth. If we have an object right here, that object will experience a force towards the center of the Earth. So we're going to draw a line towards the center of the Earth. If we have an object here, it will experience a force towards the center of the Earth, that direction. If we have an object here, it's going to experience a force towards the center of the Earth in that direction. We just keep going. We can draw lines all the way around. Wherever we put an object, that object will always experience a force towards the center of the Earth. Let's keep going. These lines represent the gravitational field around the Earth. Now if we have another object, say the moon, say this is the moon. The moon does not have as much mass as the Earth, so the strength of the gravitational field is not going to be the same. The direction is going to be the same. If we put anything around the moon, it's always going to experience a force towards the center of the moon. But the gravitational force or field around the moon is less than the gravitational field around the Earth because the moon has less mass. So this is the gravitational field around the Earth. This is the gravitational field around the moon. And characteristics of these field lines. The direction of the field lines is the same direction as the gravitational force. We put an object anywhere around the moon or the Earth, it will always experience a force towards the center. The density of the field line represents the strength of the gravitational field. Notice the density, how tightly packed these gravitational field lines are greater than the density of these gravitational field lines. So the density is greater around the Earth than the moon. Also, if we would take, say, a square like this square right here, notice there are almost three lines in there. If we move out further away, put that same square about there, we only have about one line going through that square. So the further away we get from the Earth or the central object, the less dense the lines are, which means the less the gravitational field is. And that's it.